Okay, good morning, everyone. I think it's 10:10 officially, time to start. I hope you're all doing well. My name is Teresa Hanan. I got my PhD here at Berkeley in 2024 in mechanics and dynamics. And since then, I've been an assistant professor in mechanical engineering at the American University of Beirut in Lebanon. But I've had the pleasure for last summer and this summer to teach ME 104 here. I did many times at Berkeley. I've taught it here also. I love this class, and I hope we have a wonderful time this semester. It's a lot. There's going to be a lot to learn. It's a heavy class, so we're going to have to be focused, study day by day, solve all the problem sets. So my plan for today is we're going to go through a little bit of the syllabus, the class resources for the first few minutes, and then we'll dive right into the course material. So I'll do that, and then I'll see if we have any questions, okay? Okay, so I have a notes website. That's kind of informal notes. I'm constantly updating it. Well, first of all, have you all got access to this website? This is the URL. It's not the best, but I kind of didn't buy a URL. Okay, so this is it, the course website. Lecture notes are here. Again, they're not perfect, but if you find any mistakes, please fill this form, let me know. We have official textbooks. It's stated in the syllabus, and this is kind of as an extra resource. What I'm trying right now to do is to add a few problems and videos in between the notes, so making it a little bit more interactive. Okay? So today our plan is to cover kind of up to this, part 7, chapter 7. Okay, so we'll be using Gradescope for homework submission. Did we all get access to Gradescope? Yes? Anyone did not? Okay, so all the homework will be posted on Gradescope. I think we'll make it due on Saturday evening every week. And we'll have 10 homeworks for the 10 weeks, no matter if we have an exam or not. The exam schedule is already posted here, so our first exam is in 3 weeks on Thursday here in this class. 3 weeks after that, we have our second midterm, and then the final is the last day of class. The exams need to be taken. You need to be here in person to take the exams. This class is optimized for in-person learning. I prefer that you be in class. However, you can not attend. I'm posting the lecture recording, so unless we get any technical difficulties, which has happened before somehow, sometimes the mic stops, the camera stops. If that doesn't happen, then I'm posting the lectures on B courses and on YouTube. So you can attend the lectures online. Everything, the website is available to everyone. However, I do prefer that you attend in person. We'll talk about the quizzes in a bit, which are meant to boost your grade and help you learn, actually. Okay, I have a set of previous exams. You might want to look at them before your exams. And these are interesting advice from students who have taken this class before, so read it. I think most of the advice tells you to come to office hours if you have any questions. So I'm the professor, I'll be teaching the class, I'll have office hours, and Meghana is the GSI. Meghana, do you want to introduce yourself?
Hi, I'm Meghana Sanjay. I'm a grad student here at Jacobs. I'm doing my master's in design engineering, and I have a background in architecture as well. Really happy to be with you all and assist you in any way I can. I have my office hours posted. It's 2 hours a week, and the professor has separate office hours.
Thank you, Meghana. I'll add the link to Meghana's office hours here. Okay? So, right. Any questions so far? Okay. Our calendar, I'm also working on fixing that. The first few weeks are fine. First couple weeks are fine. Okay, the office hour schedule also is here. We have Meghana, we have Ninad, who will be helping us in the discussion section, which is on Wednesdays from 10 to 12:30. That's syllabus. Okay, so this is my email, lecture time, office hours. My office is in Echeverry Hall, 6185. Okay, so basically I'll have office hours after class on Tuesdays and Thursdays. And I'm open by appointment online. If you need anything, just email me. Okay, don't worry about it at all, just send me an email. Meghana's office hours are here. I mentioned that the class will be recorded. Okay. Gradescope will have ed discussion. So did you guys have access to ed discussion? Raise your hand if you did. Yes? Anyone did not? So I kind of want this class to be active, so if you tell me if you have gotten access. Okay. I've asked more interesting questions in a few minutes. Okay? So you can read this about ed grading. So I have two grading options. Basically, I will calculate your grade according to both of these options at the end of the semester, and whichever gives you a higher grade, you'll get. Notice there's one option where no in-class quizzes are taken into account. One was the in-class quizzes, that's 20%. And that's really meant to be a grade booster for you guys and practice. So sometimes I'll announce what the quiz is going to be about. Sometimes we're going to explain something, practice, and have a quick quiz about it, just so that we maintain focus and keep up with the class. So you need to study daily. Almost every lecture, if not every lecture, we're going to have a short quiz, which you're going to scan and upload to Gradescope just during lecture. So be ready for that. Okay. The lowest 3 quiz grades will be dropped. I'm not giving any makeup quizzes, so that's meant to accommodate any absences. So take this into account, dropping the lowest 3 grades to accommodate any absences. We might also have quizzes in the discussion sections, so attend those too. The homework you can do in pairs and submit on Gradescope. That's not a problem. Actually, I'll give you a minute to get to know the person, people around you, ask where they're from, what they're doing, and if they're interested in pairing up for homework. Go. Okay, we'll continue with class right now, but you'll have more time to talk later, okay? Problem sets. I have problem sets kind of for every topic, and they're on the course website in the schedule. In the calendar. I'm also planning to add them to the notes. I have a few solution videos, so they'll be, like for example, if I click on this one, it works. So let us see. For example, no solution videos here. Next one. So on average, I try to have one solution video per problem set. You can click on it, and it'll help you out. We're going to try to solve most of these in lecture and in the discussion sections. You will not need to submit this. It's not a homework, but you need to do it. It's highly, highly, highly recommended that you do this. That's your basic practice. Your homework goes an extra step. It includes this plus visualizations using MATLAB or Python to visualize the dynamics of systems. And the homeworks are incremental. I think you'll like them, and we'll discuss them as we go through the class. So again, the recommended problems you do not need to submit, but you need to solve. And if you have any questions, let us know. I have the final answers for each problem here at the end, so that you can just, if you don't get to the answer, let us know. I also don't just care about the answer, I care about the methodology you use, your notation to solve these problems, and we'll discuss this in a few. Okay. Does that make sense? Any questions? Okay. I'm trying to add this to the notes and with the solution videos, but we'll see how it goes. Okay, where were we at? Syllabus. Okay. Okay, study groups. Work together. It's going to be helpful. So this is the textbook. It is available for free through the library website. Were you able to download it? Yes? Yes? No? Any issues? I double checked today and you should be fine. If you have any issues, let me know after class. You had issues?
The issue I ran into is when it says like log into your institution, I just couldn't find you separately.
Oh. I think log in through the library and then search from the library website for the textbook. That should work. Okay. Honor code, you're supposed to abide by the UC Berkeley honor code. And we'll try to use active learning in this class. You can watch the kind of samples here, but you'll experience it. Any questions? Yes?
Yeah, sorry if we went over this, but just to clarify, can we quickly go over the calendar and clarify which stuff is due before class on that day that it's listed, and what stuff is due after class?
Nothing is due except for the homework. And then in class, we'll cover these sets. Actually, that's a great question. So to clarify, in class today, we plan to cover these sets. So after class today, you should be able to solve these 3 sets. Okay? And then in the exercise session, we'll practice some of these sets you see here. And by Thursday, you should have solved these sets, kind of thing. And then on Thursday, we learn how to solve these 2. By Tuesday, you should have solved them on your own.
Okay, so we can do the problem sets after class, but then is there anything we should come to class having already done?
No.
Okay.
Yeah.
Thanks.
Just be ready, solve what you review and solve the previous sets, the sets related to the previous lecture. Okay? And then the homework, no matter what, is due on Saturday every week. And that's posted on Gradescope. Okay? And if we have a quiz that's pre-announced of a certain topic, I'll let you know. Okay? Any other questions? Questions? It is a lot of websites, so I should expect more questions. No? Okay, then we'll start. And if any questions come up, you let me know. Okay, so I want to start today with 2 topics that have to do with statics. That's basically not dynamics. That's a review of statics, but it's very, very important. So let's review this and we'll practice, okay? So free body diagrams, we know what those are, right? Yes, raise your hand. Yes, good, okay. So maybe you're familiar with this table. This is from a popular statics textbook, Hibbler here. So it gives us types of connections and then the reaction force from each connection. So if I have a bar connected by a cable, if I want to draw the free body diagram of the bar, what are the forces acting on the bar? Yeah, one force due to the cable. And what is the direction of that force? Along the cable, right? What other types of supports do we know? Okay. How do we turn the lights on? Here. Oh, works. Okay. And hide screen. We'll try our best. Okay, so I have a bar connected by a cable. How do I draw the free body diagram of the bar? Arias? Yes. Yeah, I have a force, a tension force from the cable, right? So this is a tension force. And its direction is along the cable. Are we familiar with this notation for forces? So are we familiar with this notation? Yeah, forces are vectors, right? What I'm going to use in this class is this or this. And I would like you to use that too, because we're going to reserve the top of the vector for other accents. So the number one thing we do when we're drawing free body diagrams is we're going to need to isolate the system. So I will never draw the cable and the force. I will remove the cable and draw the force. So I need to select what my system is. Okay, so these are our important notes for now. Okay, can you see the board? Any questions? Okay, if I have a bar, that's connected by a pin here and then by a roller here. If I want to draw the free body diagram of the bar, yes?
It's kind of dark in front. Is there a light?
Is it better? Okay, great. Okay. So this bar connected, let me call this side A, this side B. Connected by a pin at A, by a roller at B. Supported by a pin at A, by a roller at B. How do I draw the free body diagram of the bar? Yes. Normal forces on A and B. Is that it? Yeah, the force at A is going to have X and Y components. Why is that? Yes?
It restricts that motion.
Exactly. So I can call that AX, AY, B, or the normal force at B, BY. Instead of this, I can draw a vector, a force that's oblique, where the direction is to be determined, as long as the force at A has two components that need to be determined. Again, why does the force at A have two components? Because the pin restricts motion along the horizontal and the vertical, so in both planar directions. So that's why A has two components. The roller on the other side only restricts motion along the vertical, so that's why the constraint force is along the vertical. So notice this chord here is a constraint. And whenever you remove a constraint, you need to replace it by a constraint force. A constraint is enforced by a constraint force. So that we can consider also here that the pin and the roller, they're constraints. And these constraints are enforced by constraint forces. So whenever we have a direction of translation that's constrained, we're going to have a force in that direction. Constraint, we get a okay. Questions? Does that make sense? Say, for example, I have a cylinder on the corner, laying on a corner that's oblique. If I want to draw the free body diagram of this cylinder, what are the forces acting on it? How many forces are acting on the cylinder? 2, right? If I add the weight at the center of mass, that's going to be 3. But I have 2 forces. What are the directions of these forces? Show me with your hands, kind of. Yeah, normals. and A and B. Why is that? Because the motion of the circle or the cylinder is restricted along this direction and along this direction. Does that make sense? Okay. Now if I have a beam totally fixed to the wall like that, how do I draw the free body diagram of the beam? I'm assuming that gravity acts vertically down. So I'm going to need to include the weight here. So this is the beam, isolated from its support. How many forces are acting on it? Okay. Okay. Did you have a question? Okay. So we have the weight force, right? What other forces do we have acting on it? Yeah, I'll call this point A. I'll call A is one force, or random directions, or one horizontal, one vertical. Is that it? There's a what? A moment, a reaction moment, right? Why do we have a reaction moment? Yes?
Because the weight makes a moment in the clockwise direction.
Right. Yes.
It's because there's horizontal displacement between the weight and the point we're looking at.
Yes. But also because the support restricts what?
Rotation.
It restricts rotation. So whenever you have a restriction of rotation, that's going to be satisfied or enforced by a moment, a constraint moment. So whenever whatever. Okay. Questions? Okay, so I've got set 0, which is posted on the website. I think it is. So if you have your iPad, you can open that here. If not, I have hard copies of set 0. So let's start and solve as many as we can in like 15 minutes. And you can work on that with your neighbor, and I'll pass it around and check. I might ask you to come to the board and write your solution if you're okay with that. Okay? So set 0 is posted on the website, and I have some hard copies. Raise your hand if you prefer that I bring you hard copies, just so I can get a count in my hand.
This is color.
Okay. Okay, sounds good. Thank you. So yeah, let's give it 10 minutes to solve these. It should be pretty quick. So you have your system, you just want to draw the free body diagram. Yes. You're welcome. Thank you. Does anyone still need a paper? You're welcome. Any more papers needed? Okay.
Thank you.
You're welcome. You're welcome. Okay, so let's start with the first one. This is quicker, probably. And remember, forces are vectors, so you need to put the vector kind of force. That's great. Do you want to name the force and underline the vectors? Don't forget to underline the vectors. So vectors are underlined, scalars are not, and there's a big difference between the two. So we need to make this distinction in our notation. It's very important. if you have any questions, just raise your hand.
For drawing on free body diagrams, do we have a convention for like starting the vector at its base or at its
The force is a sliding vector, sure. Yeah. Yeah.
This one is on here.
No, it doesn't matter because the force is a sliding vector, so yeah. You kind of want to see what you're doing. Okay. Yeah. Could you actually use this? Because I did rename the vectors.
Oh.
Can I see? Okay, good job. Can you actually maybe use this because I renamed the vectors and then underline them. But, okay. Okay, so please double check your neighbor's answers. Let me know if you have the same answer or not. So make sure they've underlined the vectors, named the vectors, underline them. And I think we're done with the first page. Not double check. Any questions? Any questions? Yes.
For this one, the two circles, is
That's a good question. So if let's do number 5 is I skipped 5. Let's do 6. So 6 looks like this. Oops. Okay, that's why I give you the. I'm not a good drawer, so that's why I give you the papers. Okay. So if I want to draw the free body diagram of A alone and B alone. So that's disk A. That's disk B. How many forces are acting on A? So that's 6. Yeah. How many forces are acting on A? 4. What are they?
The weight, the 2 normal forces from the stick,
Yeah.
and the normal force from the other circle.
Okay. And then what forces are acting on B?
One weight, normal from the circle.
One weight at B, one normal. What is the relationship between these two normals?
They're equal.
Equal but opposite, right? Equal in magnitude, opposite in direction. Why is that? Newton's third law, right? And then we have a normal force here and 4. I think that's it. Now if I want to draw the free body diagram of the system of A and B combined, A and B together, so I'll erase this. If I want to draw the free body diagram of A and B together combined, what forces do I include in this free body diagram? Or easier question, which force do I not include?
Normal force between the 2 circles.
Exactly. N3 and minus N3 is going to cancel out. So I'll just add N1, N2, N4, and the weights. Okay. Raise your hand if you kind of get this. Like, mostly. Questions? Questions? Okay, for part 7, what is this thing at A? Yes. A torsional spring. And what is its effect? A moment. It gives a moment. Okay, let us skip to 10. Oh, I'll erase the board here. Okay, so this is part 10. It's a pulley system. If I want to draw the free body diagram of this mass, what are the forces acting on it? Exactly, the weight force. What else? The tension force, vertically up, right? What is the relationship between this tension force and P? Yes. So what is the relationship between this tension force and P? So these are 2 chords. This is a chord. This is another chord. Any ideas how to start? How to find the relationship between T and P? Yes. Yeah. Then what? Yes, I think it has to do with the pulleys. So if I take this pulley and if I draw its free body diagram for this pulley, I have 3 strings coming out of it and 1 string going down. I know that the force in this string is minus T. Okay? And then I have this cord. This is 1 cord. All of that is 1 cord, right? Does the tension in the cord change in magnitude? No. Assuming that the cord is massless, the tension force, and mass is an inextensible, the tension force in magnitude is not going to change throughout the cord. So what are these 3 forces? What are the tensions here, here, and here? P or minus P, actually. Minus P, minus P, minus P. And assuming that this pulley is massless, then you can now use what you've learned from statics. F is equal to ma, but m is 0, so F is equal to 0. So that's a statics problem. Then what's the relationship between T and P? Well, minus T minus 3P is equal to 0. So T is equal to minus 3P. T is equal to minus 3P. That's it. Does that make sense? Okay. Make sure your neighbor understands this by doing the free body diagram of 14. 14, then we'll do 1 more and that's it. Yeah. So you're doing 14 right now, and if you have any questions, let me know. So yeah, I think you can relate the tensions to the weights, right? So W1, W2, the tension, which is the sum of these two, right? And this is T1, this is minus T1.
Right.
W5, T2, which is the sum of these two. Yeah, good job. Do you want to do 13? Let's assume the pulleys are massless.
Oh, massless.
Yeah. Did I make a mistake? T is equal to 3p. T is not 3p because T is pointing up and P is pointing down. So you have to have opposite signs.
This system.
So, I'm sorry, I'm just going to put this in. Okay, so what are the forces acting on, what is the free body diagram of M2? W2 and a tension force, call it T1, right? What about for M3? How many forces are acting on M3? 2, right? What are they? Weight and tension. Any relationships between these two tension forces? They're the same, right? Why? Same core, T1. And then for the last one, M5, I have W5, right? And T2. Any relationships between T1 and T2? Yes?
The tension force generated by M2 and F3 is equal, added together is equal to T5.
How did you get that?
Because that one string sustains the other two strings.
Right. Or we can draw the free body diagram of the pulley. Okay, if I draw the free body diagram of the pulley, what are the forces acting on it? Minus T1, assuming pulley is massless, so no weight, and T2. So we get that T2 is equal to 2T1. Yes?
Why is it M2, 3, and 5?
I don't know, that's what they have here. Maybe in the original problem the pulleys had masses. I just took interesting system setups from different problems, but we're just doing the free body diagrams here. Any questions? Okay. Yes.
For both weights, the tension for weight 2 and weight 3,
Mm-hmm.
tensions are the same if they're on the same string.
Yes. Yes. Other questions? Yes.
For the question to draw the free body diagram of each pulley, would we also just include that?
Oh, I asked for the pulleys. That if you want to draw the free body diagram of that, this pulley, and for that pulley, you would do T2, sorry, no, minus T2, and some force here. Okay? Does that make sense? Have you double check? I think so. Yes. Other questions? Questions? Okay. So free body diagrams, really important. Forces are vectors, underline them, and isolate your system. So remember, I don't draw the supports when I'm selecting my system, I isolate it. Okay? Any questions? Yes.
So for the left side, it's the same as the right side for T2?
What do you mean? The T2 force is the same throughout. So when I use the same name, then it's the same force.
Even though M2 and M3 act on the left side?
Yes. So let me see if this answers your question. Here I have, for these two, I have W2 and W3. T1 and T1 are the same. Now, if these two masses are the same, then you have equilibrium. And yeah, you have equilibrium. If the two masses are not the same, the tension is still going to be the same, but you're going to have accelerations. Yeah. But we're going to talk about this. We're going to solve these kinds of problems in next week. Other questions? That was a good question. Yeah. So, other questions? Okay. What I want to go over next is a review of vectors, a quick review of vectors. Okay. Oh. Okay. If I have a vector A, I can scale it, right? So what is the vector 2A? What is the vector 2A? It's a vector which has double the magnitude, right? 2A. If I wanna flip the vector, what operation do I need? I'm scaling by -1, right? Minus A. I can also get half A. So that's scaling a vector. E. If I have two vectors now, A and B, how do I add them? So what is A plus B? Is that a vector or a scalar, A plus B? It's a vector, right? So here, A is a vector, 2A is a vector, right? Minus A, also a vector, half A is a vector. What about 2 on its own? It's a scalar, right? I don't underline it. So I can scale vectors by multiplying by a scalar. So A is a vector, and K is a scalar. Now for two vectors, there are many operations we can do on two vectors. We can add them, we can subtract them, we can calculate the dot product or the scalar product, which is going to result in what? The scalar product, a vector or a scalar? A scalar. What about the cross product? A vector. Okay. So how do I add two vectors? Without the components. I haven't reduced components and bases yet. Yes?
Like the tip to, or like
Yes.
the tip on the...
I can put the tip to tail. So A plus B is this vector, A plus B, right? So that's one way to do it, putting tip to tail. Another way to do it is, does anyone know any other ways to add vectors? The parallelogram rule, completing the parallelogram, have you heard of that? So I have A, B, I can complete the parallelogram here, and that's going to be A plus B. Same thing. Good. Okay, how do I subtract two vectors? So what is A minus B? Yes? Exactly. So I have A, I have B. I want to add A minus B. So A minus B can be seen as adding A to minus B, where minus B is this vector. Okay, or this vector. So that's A minus B. Or if I complete the parallelogram, it's the other diagonal. A minus B. Okay? Does that make sense? Questions? Questions? Okay. What about the scalar or the dot product? If I take two vectors, A and B, what is their dot product by definition equal to? What is the definition of a dot product? Yes?
The magnitude of A times magnitude of B times the cosine.
Exactly. So that's A, that's B, and that's theta, the angle between them, and the magnitude of A, magnitude of B, and cosine theta, the angle between them, that's A dot B. Raise your hand if you knew this. Great. Why don't you say so? A dot B is magnitude of A, magnitude of B, cosine theta. Okay. Is A dot B the same as B dot A? Yes. Why? Yeah. So B dot A is magnitude of B, magnitude of A times cosine minus theta. But cosine theta and cosine minus theta are the same. What else? What is A dot A? What is that equal to? Magnitude of A squared. Because that's the magnitude of A, magnitude of A. And what's the angle between A and A? 0. And what's cosine 0? 1. So the magnitude of a vector is the square root of the dot product of the vector by itself. A dot A. When is questions? Questions? When is A dot B equal to 0? Notice that the dot product is a scalar. It's not a 0 vector. It's a 0 scalar. So when is the dot product of two vectors equal to 0? When they're perpendicular or orthogonal, right? If A is perpendicular to B. Let me write that here, because I need the space. Okay. The scalar product can be seen as a projection. Okay. First of all, let me introduce what a unit vector is. What is a unit vector? Yeah, it's a vector with magnitude 1. So let U be a unit vector. So what is U dot U? 1. Let me go back here a little bit. So if I have A and I want to obtain a unit vector in the direction of A, what is that? Unit vector in the direction of A. I have to divide A by its magnitude, right? So that's A over the magnitude of A. And that's a unit vector. Because if I take this vector dotted with itself, I'll get the magnitude of A squared over the magnitude of A squared, which is 1. Make sure your neighbor understands this. Double check, double check. Take a minute. All's good? Questions? Okay, so the dot product is a projection. If I have a vector A and a unit vector U, what is A dot U equal to by definition? Magnitude of A magnitude of u, which is what if u is a unit vector, 1 times cosine theta, the angle between them. So notice that this is equal, I'll extend this vector to make it a little bit more obvious or clear. So magnitude of a cosine theta, if I consider this right triangle here, what is the length of this side? What is it? Exactly, because of trigonometry, right? That's a right triangle. This side has magnitude a cosine theta. Let me take another unit vector, v, that's perpendicular to u. What is the length of this side? A sine theta. Do you agree? Do we agree? Raise your hand if you do. Yeah? So now I can write the vector A as the sum of this vector and the sum of this vector. So I can write A as the magnitude of A times cosine theta along u plus sine theta along v. You've done this before, right? Yeah? We'll do this a lot in dynamics. You've done it a lot in statics, mechanics, probably. Okay. Questions? Cross product. Any questions before we move on to the cross product? Okay. If I have two vectors, A cross B is equal to what? First, let us see what the magnitude of the cross product is equal to. So the magnitude of A cross B is equal to what? We'll do magnitude, then we'll do direction, because the cross product produces a vector with magnitude and direction. So what is the magnitude of the cross product?
Product of the magnitudes times sine.
Exactly. So that's A, B, theta, that's the magnitude of A, magnitude of B, and I'll put an absolute value of sine theta. Sorry, absolute value of sine theta. So I'll get the positive magnitude of A cross B. What is the direction of A cross B? Perpendicular to both, inside the page or outside the page? Inside the page here, right? How is the direction of A cross B determined? By the right-hand rule. So the direction, so A cross B is the magnitude of A cross B along n. This is a unit direction determined by the right-hand rule. Right-hand rule. So I take my right hand, I put my fingers along A and I curl them towards B, and my thumb is going to point along N. So take my right hand fingers from A to B curling, my thumb is pointing along N. Okay? So then B cross A is outside the page, right? A cross B is inside the page. Let me try this. If I put A cross B like this, is it inside the page? A cross B. Is that inside the page or outside the page? Inside or outside? Raise your hand for inside. Raise your hand for outside. So what is it? Inside. It is inside. Any questions? Questions? That's important. Okay. So that's the cross product of two vectors. Notice I haven't introduced a basis yet, but let's do that now. We're familiar with the Cartesian basis, I, j, k maybe, ex, ey, ez, we'll do that. So we're going to introduce a coordinate system. It's orthonormal. What does that mean? Yes?
Each basis vector is orthogonal and also unit vector.
Exactly. And it's right-handed. What does that mean? What does that mean, right-handed?
Coordinates defined according to the right.
Exactly. So if in a certain order, if I cross I cross j, I'll get k. So usually in textbooks, you see those as I, j, k. In this class, we will reserve lowercase bases for moving bases and then uppercase for fixed bases. So uppercase for fixed bases. Okay, so for now, we'll just think about fixed bases, and then on next Tuesday, we'll start introducing moving bases. Actually, we might do that a little bit now also. I won't only use this. Equivalently, I will use EX, EY, EZ, and then the fixed correspondent EX, EY, EZ. I'll also use E1, E2, E3, E1, E2, E3. That's all the same thing. Is this a right-handed basis? For it to be right-handed, I'll need that E1 cross E2 is equal to E3. Is that the case? Yes. Can anyone guess which one of these bases is my favorite? Option A, B, or C? C. Why? It's just generalized is better. You can imagine this in n dimensions, not just in 3 dimensions. That's an advantage of it. The other advantage is that if I want to express a vector in this spaces, for example, I'll write vector A is AX, EX, plus AY, EY, plus AZ, EZ. And that's vector A having 3 components, one along E1, EX, EY, and EZ. And there's a better figure in the notes. If I write it in terms of E1, E2, E3, I'll write A1, E1 plus A2, E2 plus A3, E3, which can be written as just the sum of AI, EI. Are we familiar with this notation? Sum I equals 1 to 3 of AI, EI is A1, 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 E1 plus A2, E2 plus A3, E3. So this is often used in continuum mechanics. We will use this notation later on in the class. So keep it in mind. Right now, I think mostly I'll use this. We'll introduce other bases next week, like the cylindrical polar coordinate system, the Serif-Frenet basis. So we're going to introduce more bases. The general rule is that if the basis vectors are capitalized, then it's a fixed basis. If it's a moving basis, then we'll denote it by lowercase letters. And we can express vectors in terms of bases. Okay? Any questions? So now I can go back to the dot product, and I can take the dot product of two vectors, now expressed in terms of their components. So go back. Okay. So say I have two vectors, ax, ex, plus ay, ey, plus az, ez, b, bx, ex, plus by, ey, plus bz, ez. How do I calculate a dot b? I can actually write a dot b as a So I'm just replacing what a and b are in terms of the ax, ay, ez basis, the Cartesian basis. Okay, and to calculate the dot product, I'm going to distribute. So how many terms will I have when I distribute the dot product? 3 here and 3 here, and I'll distribute. I'll get 1, 2, 3, then 1, 2, 3, and then 1, 2, 3. So how many terms in total? 9, right? But out of these terms, how many are going to survive the operation? How many are going to be non-zero? Just 3, right? Because what is ex dot ex? 1. Why is that? Ex dot ex is what? 1, because ex is the unit vector, right? What about ex dot ey? 0, because they're perpendicular. Ex dot ez is also 0. So I'm only going to have 3 terms left, which are going to be the ax, bx, ex dot ex, which is 1, ay, by, plus az, bz. Questions? Oops, where? Oh, just don't need to do that. Let us go to the cross product part now. Ooh. What is ex cross ex? Why? 0 vector or 0 scalar? Right. Why? Yes, because the angle between a and a is 0, sine 0 is 0. So whenever I have two vectors that are collinear, their cross product is going to be 0. What is ex cross ey? Easy, because ex, ey is a right-handed basis. Okay, ex, ey is a right-handed basis. Ex cross ey is going to be easy. Ez cross ex, ez cross ey. Well, first, ez cross ex is what? Ez cross ex is ey. Ez cross ey, negative ex. So to see this, you might want to draw the right-handed basis, ex, ey, ez, and then double check. Ez cross ey is going to be minus ex. A shortcut for this is to actually draw ex, ey, ez cyclically like that, right-handed. So now if I go ex cross ey, I'll get ez. But if I go against the arrows, then I'll have to put a negative sign. So what is ey cross ex? Ey cross ex, negative ez. right? Okay. So I can use this to change the dot product, so I won't copy it again, but I can change the dot product to a cross product. And then I'll need to evaluate EX cross EX, 0 EX cross EY, and so on. How many terms will I get? How many non-zero terms will I get from the cross product? Not 3. Think about it, think about it. You can chat with your neighbors. How many terms are going to survive? So 9 terms total. Out of these, how many are 0? 3. The EX cross EX, EY cross EY, EZ cross EZ. How many do I have left? 6. And this operation, maybe you've done it before in like this, determinant form. Maybe you've done this before. We have to be careful though. In this course, we will not always take the cross product of 2 vectors expressed in the same basis, in the same bases. So if I take the cross product of 2 vectors, one of them is expressed in the polars, the other one is expressed in the Cartesians, then I cannot put them in determinant form like this. So they need to be in the same basis to be put in this form. Agreed? We'll go through this again. Okay, let me also cover the differentiation of vectors, and then we'll do some practice. Okay. So in dynamics, usually we'll take a lot of time derivatives, d by dt, or dot. You're used maybe to, if you have f of x, its derivative is f prime of x for a function, which is df by dx. In dynamics, we'll use a lot of derivatives with respect to time. So I'm going to take a function of time, and we have a special notation for the derivative with respect to time, which is a dot. F dot of t is equal to a df by dt. Now for a vector, I'll have a vector, say A is equal to ax ex plus ay ey plus az ez. I want to calculate the derivative of a with respect to time, so that's going to be a dot. You see how I'm putting the x and the dot on top of the vector? So that's why I kind of wanted the underline instead of the arrow usually do. Okay, so what is a dot, the derivative of the vector? So in general, the most general sense, I'll have to use the product rule because ax and ex, this is a product of 2 terms. But here, is ex a function of time? No. So what is the derivative of ex? 0. So that's the importance of stating that the ex, ey, ez basis is fixed. We will deal with bases later on which are not fixed, and their derivatives are not going to be 0. So I'm going to write this in general. uv dot is u dot v plus v dot u. So a dot x ex plus ax ex dot, but this is 0 because this vector is fixed. 0 vector. Plus a dot y ey plus a dot z is. The derivative, any questions? Okay, so I'm going a little bit fast, but we'll do an exercise in a couple minutes. The derivative of the dot product, d by dt of a dot b uses the product rule. A dot b plus a dot b dot. And the derivative of the cross product also uses the product rule. Okay. One more thing you should know are the sine law and the cosine law from geometry. We're going to use these a few times in the class. Have we heard of these? sine log, cosine log, they are summarized in the notes. Okay, so I won't go through them right now. What I want to do is I want to give you set 1, which you also have on the website, set 1. And let me decide which problem. Well, first you can take one and pass set 1 if you need. Okay. I might not have enough for everyone, so I'll have you figure it out. Okay. Okay, so set 1, we'll do some of these problems in the exercise set in the discussion section tomorrow. What I want to do right now is problem 5. So please go ahead, start with problem 5. It's going to be a pair work quiz, and I'll give you 20 minutes to do this. I'll set it up on Gradescope right now. Pair work quiz. If you need a paper, I have papers here, and if you have any questions, I'll answer those in 2 minutes. So problem 5. Did I say 5? Yeah, 5. 5 pair work quiz. 20 minutes. Set a 20-minute timer. Pair work. Choose a pair. Yes. Yes, that's fine. Do not use AI though. That's not allowed for these quizzes. Oh, yeah. Just start with this. Sorry. It's fine if they need them. Yeah, they can take from doing that. But if you want, you can pass around and look at what they're doing.
The what?
If you want, you can pass around. If they have any questions, then you can help.
Yeah.
So I'm using the EX, EY, UZ basis. Any questions, anyone? No, the vector is not an array. You have to express it as I did in terms of the basis. Because we're going to use many bases in this class and you want to be clear about which basis you're using.
I think I did
Yeah, you cannot do this.
So is it, you want it
Yeah, you cannot write the vector as an array. You cannot do parentheses or brackets and put the components of it. Because in this class, we will not just be using one basis. We will use many bases. So you have to be clear about which basis you're using. So you have to use this notation over there. So like 1 ex minus 2 ey, 3 ez. Not 1, 2, 3. Yeah.
this is kind of
Yes. Yes. Then I don't want this. Yeah. Because we need to be clear about which bases we're using. We're going to use many bases. Yeah.
No, it's fine.
Any questions?
Oh yeah, I was wondering what you meant by like defining the basis. Is
Yeah,
that for
so
this
that
one?
wouldn't be that. That would be RA vector is 30, easy.
Oh,
Yeah. Yes, good. No, the force is a vector.
Oh, so I need to repeat.
Yeah, you
Okay,
find
sure.
its direction.
RB to A, right?
It's RB minus
RB minus RA. I know I should have wrote this in the vector, but should the vector be in the direction which the child pulls, or like should I take the vector at the B end or at the A end?
No, B. Because,
Okay,
yeah.
sure.
So the tension pulls down,
Okay,
points
sure,
down.
got it.
Can I see?
Yeah.
The force is a vector.
Oh.
So you cannot have it just to be 70.
Okay. Oh.
Where are your answers here? This one?
Over here.
Can you maybe, this is a blank piece of paper. You can write everything.
Sure.
Yeah. Have questions? Yeah, same thing. Yeah.
How'd you draw minus vector?
The minus.
Because I didn't see it because it's kind of far.
Oh, I'm sorry. Can I have your pen?
Yes.
So this is A, this is B. Okay, I can do A and plus B. I add B to it, I get A plus B, right? Or I can do A minus B, and I'll get A minus B. So you add the opposite.
Thank you.
You're welcome. Okay, this. Yes.
Point of reference we're using for the tension vector?
The tension is like pulling out at B.
Okay.
Yeah, so it's pointing like
Eight
like
B.
that.
Okay.
Sorry. Yeah. So underline the vectors. Underline your vectors. Any questions?
Yeah, I'm wondering like for, maybe I did this wrong, but I said that's what our BA would look like.
So RB with respect to A is RB minus A. That's correct. So it's the vector from A to B.
And then I guess like,
The tension force.
oh, I see, if it were like moved up. Okay, so does it need to start
Yeah.
the portion? Okay,
Yeah.
thank you.
Can I see?
Sorry, I missed the first half of your class.
Oh. Okay, so are you familiar with vectors at all?
Yeah.
So what is the vector at A? Can you draw it? It's from O to A. So you just draw the vector from O to A.
Yeah.
And it's along
And then-
EC, and it's like 30. So it's 30 EC.
Okay, yeah.
And you can do RB.
This is
RB is from O to B. So it's this along EX, and this along EZ, and this along EY, or minus EY. Yeah, so be careful. Be careful, everyone. The force is a vector. So you cannot say that the tension is 17 newtons because the tension is a force, which is a vector. So you have its magnitude and you have its direction. Yeah?
I'm confused what it's asking about we're confused what it's asking about. Does it point from B to A or A to B?
Like the vector RB with respect to A. Is it from A to B like that, or is it from B to A like that? So the base at A, tip at B, or tip at B, base at A?
Like, if you're doing tip to tail, which one do you start with, and then which one do you go to?
No, just the vector RB minus RA. So that's actually RB minus RA is from A to B.
B minus.
If you draw RA, draw RB, and draw RB minus RA, that's what you get.
Right, because B minus A is like some vector down here, right?
Which is the same as the vector.
Oh, so it looks like something that's A to B.
Yeah.
Oh, okay, I get it. Thank you.
Yeah.
Direction. How do we know the direction that the child pulls?
By the way you add or you subtract. So if you're putting head to tail, so let me see. Can I borrow this? Okay, here. So I have A, I have B, and I'm summing. I'll put A plus B, and that's A plus B. Then you know the direction of A plus B, right? The direction of A minus B is going to be like that. So once you do that here, you'll figure out that RB minus RA is going to be from A to B. It's going to be like that, pointing down. And RA minus RB is going to be pointing up. How do you determine that? From the definition of how you do sum and addition and subtraction of vectors.
But the 70 newtons.
Oh, the 70 newtons is pointing down. But the child is pulling on the cord down, so the cord is in tension. So the force at B is 17. But it's not, the magnitude is 17, so you have to add the direction, right?
Yeah, that was before.
Yeah. Okay. And if you're done and submitted, you can do the previous problem for. Sorry. Yes.
Okay. I'm confused about the tension force. Is the tension force the force that opposes the kid pulling, or is it just the kid pulling?
It's this.
So it's
this. Yeah.
It's this.
Yeah.
So then it's the other side. So that's RBA.
Questions?
I can't think of anything else other than.
No, you have to put the direction of the tension force.
Oh, the
So
direction.
yeah, so this is magnitude, and the direction is a unit vector from B to A, right?
Yeah.
So how do you find the unit vector along this direction?
Don't you just normalize the.
Yeah, you normalize the vector you already calculated before. Yeah. Does that make sense? So TB minus TA, sorry.
Oh
I'm
wait,
gonna
so you
put-
just normalize A to B and then.
Normalize A to B, yes. You get the unit direction. Yeah. Any questions? That's good. Okay, how much more time do we have? A sketch is good. Sketch is fine. Tough sketch, yeah.
And for number C, it says here, does it point from A to B? So it's just like, do I have to explain in words?
Just say A to B or B to A. Yeah. Okay. Less than 10 more minutes to go. Yes.
Like fully reduce the vector. Do we have to like factor out the 70?
Yes.
Okay. So the force is going towards like right, because he sees a pole from this way. So we know the magnitude is 7, right? You can't do that off the top of my head. Trying to ask what is the tension force? So we know the magnitude is 70 newtons.
Mm-hmm.
We know the direction is pulling from A to B.
Mm-hmm.
And then from there I'm lost.
So the direction is from A to B. You know the magnitude, and you need to add a unit direction, right?
Yes.
So what's the unit vector from A to B? How do you calculate it?
It should be, that one points from B to A, this one points from A to B.
Mhm.
So it's this one, you know?
Mm-hmm. Over.
Over,
This is not a unit vector. So how do you
Yeah.
make it a unit vector?
it's that over its magnitude.
Exactly.
Okay.
Yes. Yes.
Do you just want us to express the force and then the direction like this? Or
The force vector is 70 times the direction, the unit direction. And you have to underline the vectors and using capitals. EX, EY, Z here. Excuse me.
Sorry.
Yes.
Okay, so then if the tension is the kid pulling and
Mhm.
it's RBA, so then that's the
RB relative to A, yeah.
yeah. So then that's the because that's like the direction.
Yeah, but that's not a unit vector. So now if you calculate the magnitude of the tension force, it's not 70, it's 70 with magnitude.
Oh
of
wait,
this.
so that's the vector. So
Yeah, you have to
I
make it a
do-
unit vector.
So divide
Divide by its magnitude.
divide by 70.
No,
Or-
its
divide
magnitude
by
of,
the vector.
yeah,
Okay,
the
got it.
length from between.
can I just do this and
What? Yes, fine. Okay. So just going back to the question you asked me, are B minus are A points from A to B, right?
Yes.
So that's the vector you want to normalize.
Yeah.
B with yeah. Okay, cool. Okay, couple more minutes to go. You should be all submitting. Anyone still needs more time? Think we should be good? Can you do in 2 minutes? If not, let me know by the end of lecture. At the end of lecture. Time is up.
I don't just see it on my first
Was anyone able to submit the assignment? No? No one? Oh, 12 people did submit. Let me... Okay, if you haven't been able to submit, just put it aside. At the end of the lecture, I'll give you an extension so that you can submit, okay? Just put it aside for now, and let's continue. I want to introduce dynamics. And we're going to go from the most general case to kind of situate the class. Okay. So the dynamics, what is dynamics? It studies the kind of motion of bodies under forces. So if I consider a body, the most general body, well, not the most general, but I'm going to start with the continuum. So this is called the continuum potato. And I have forces acting on it, F1, F2, maybe force distributions, moments. So consider a general continuum, and I have forces and moments acting on it. Now in general, a continuum can move and it can deform. Potato. If I have a body, how do I know that it has moved? How do I know if a body has moved or deformed? General ideas. Yes. Yes, exactly. I have to compare it to something. So I need a reference configuration. I compare it to a reference. So in general, it's common in continuum mechanics to consider a reference configuration of the body. So I have my potato, and that's the reference configuration. And I have the current configuration. Okay. So the reference configuration of the body is the configuration. It could be the initial configuration of the body, or it could be any configuration that the body could possibly attain. And if I have motion of the current configuration changes with respect to the reference configuration, then I have motion. I'll explain that more. So let me consider a point in the reference configuration. I'm going to call this point X, and I'm going to call it a material point. So let X be a material point of the body. Can anyone guess what a material point means? Random guess. Yes.
A point which moves with some element of material that you're trying to track?
Right. Yes. Yes. So it's a point that belongs to the material of the body, and it does not move relative to the body. So for example, I can consider this faucet over here to be a material point on the desk. But this paper is not a material part of the desk because it moves with respect to the desk, right? So my face, you can consider my nose to be like a material point on my face. If I had an ant walking on my face, that wouldn't be a material point on my face, okay? So a material point belongs to the material of the body. So if I have a material point in the reference configuration, I should be able to track it and find the same point in the current configuration. I'll take an origin, and I will draw the position vector of the material point in the reference configuration, and I will call it x. And I will take the same material point in the current configuration, and the position vector to that point, I'll call it small x. What does the position vector mean? The position vector to a material point, we kind of just did it in the exercise right now. It's a vector from where to where? A position vector to a material point is a vector from where to where? From the origin to the material point. So this is the position vector of x in the reference configuration. This is the position vector of x in the current configuration. Notice that I have 3 x's and they're all different. This x is a material point, it's not a vector. It's the name of a point. This x, capital X, is a vector. This small x is another vector. And if this were not confusing enough, I'm going to add one more, which is chi. Looks like this. And I'm going to call this the motion function. So let me erase here, and I'll do this again here. So I have ref config and the current. I have x and I have x. I have x is the material point. X, the position vector of the material point of the ref configuration. So, any questions so far about these position vectors, what they mean? Yes?
I guess I have to ask if we do something different, if we know the object deforms, or if we use the same principles.
If the object, we use the same principles. So we will talk in a minute about what it means for a body to be rigid. So we'll talk about this. But for now, we're considering a general body that deforms, does not detach. Yes? No, they don't. You can consider kind of an elastic body, and as the body moves, it's going to deform, so the reference configuration, current configuration are the same. So there's deformation and there's just motion. Other questions? Okay, so technically, if I have a function that for every material point x, it gives me the location, its location, the position vector, then I can track the motion of the body. So that's what we call chi. So chi is a function that gives us the position vector of all the material points on the body in terms of time. So again, this is a motion function. I can tell it which material point I'm talking about. I can tell it what time it is, and it can give me x, the position vector of the material point. And it can do that for all the material points on the rigid body. So that's why I call this function the motion function, the motion. And then equivalently, instead of the material point being the input in the function, there's an equivalence between the material point and the position vector of the material point in the reference configuration. So I can write this as, the function will have a different form, but it's the same substance, xt. And sometimes we put the t as a subscript of x. Yes?
Is this function the same? Is the chi function the same as the probability distribution?
No, different, yeah. Okay. So for now, this body is deformable. What makes a deformable body, or what makes a body rigid? What differentiates a rigid body from a deformable body? Yes? Cannot deform. What does that mean?
None of the material points move relative to each other.
Right. So if I have a rigid body in the ref configuration, and I have two material points, I'm going to call them A and B, same material points A and B. Even, let me draw a moving body, actually. I'll draw this better. This body is rigid if A and B don't move with respect to each other. Can someone think of a general mathematical statement that describes this? If the body is rigid, then what's special about A and B? Yes? The vector from A to B, very close. So I can draw the vector. Okay. So I can draw the vectors from A to B. This is xb relative to A. Sorry. And this one is xb relative to A. Right? So the vector is not the same, but there's something about the vector that remains the same. Yes? Its magnitude, right. So the magnitude of xb relative to A is going to be equal, is going to be conserved during the motion. So for a rigid body, the distance between any two material points on the rigid body remains the same throughout the motion. RB stands for rigid body. Remains the same during motion. Does that make sense? If I have this body that's rigid, and I consider two material points on it, as the body moves, the distance between the two material points is going to be the same. I can also consider two material lines on the body, this line and this line. They're always going to remain parallel. So a consequence of distances being the same is that angles are also conserved. You can think about it this way. The distance between this and this is going to be the same as the distance between this and this as it moves. So the two lines remain parallel. So distances are conserved between material points. Angles are conserved between material lines. So that's what makes a body rigid. Does that make sense? Any questions? Okay. So in this class, we will only consider rigid bodies. We will only consider rigid bodies. You would consider deformable bodies in the continuum mechanics class. I remember I took that class. First class I took at Berkeley, it was in this room. So you would take this in continuum mechanics. You would learn about body deformation. Okay. So that's what makes a body rigid, which we're going to study here in dynamics. And then we're not going to start with rigid bodies. We're going to start with a simplified version, which are particles. What's the difference between a particle and a rigid body? So under what conditions can we consider a rigid body to be a particle? So this is a simplifying assumption. What's the difference between a particle and a rigid body?
Body has volume area.
Yes, but it's not just that.
Rigid body has like a set of points.
Rigid body has a set of points. Sometimes we think of a car as a point, and sometimes we think of a car as a rigid body. So it's not about the volume, it's not about the size. Yes.
So where forces can act on the body?
Maybe, kind of. Any other ideas? So, yes, it's more related to that. So let me get my rigid body here. This is a rigid body, okay? It can translate and it can rotate, right? Now a particle, can it translate? Yes. But is the rotation of a particle defined? No. So a particle is a rigid body where we neglect the rotation of the rigid body. So when can I consider a car to be a particle or treat it like a particle? When it's just translating. When the car starts rotating and I have to take the moments into account, then I have to look at it as a rigid body. And I have to use balance laws for rigid bodies. We're going to talk about this. And we're going to define what rotation means also later on in the course. But for the first few weeks, we're going to start not by studying rigid bodies, but we're going to study particles and translation, learn a few concepts, learn a bunch of concepts, and then extend this to systems of particles and then to rigid bodies. Okay? So under what condition can we consider a rigid body to be a particle? When we neglect the rotation of the rigid body. When we neglect its rotational inertia. So that's what we're going to start with. We're going to start with particles and then move on to rigid bodies moving into plane. Okay? Then you can take other advanced dynamics courses, intermediate dynamics or engineering mechanics 3 that look at rigid bodies moving in space and so on. And different, we'll talk about this later. Okay. Any questions about kind of our plan? So a few weeks into the semester, we're going to go back to rigid bodies, but right now we're starting with particles. Okay? Questions, questions, questions? Let's start. Let's consider our particle. Okay. So I'll consider okay. So dynamics is decomposed into two components, kinematics and kinetics. Kinematics has to do with like the motion, the geometry. and this has to do with forces and balance laws. So in case you see these names, you know what they mean. So I'm starting right now with kinematics. So I want to describe just the motion of a particle, not the forces yet. Okay. So kinematics of particles. Consider a particle in three-dimensional Euclidean space. So I have my three-dimensional space. So my particle P is moving in space. Okay. How do I draw the position vector to the particle? That's the vector from where to where? The origin to P. Or I'm going to call this the position vector to the particle. So again, this is the particle moving on a curve. This is the location of the particle at time t, and this is the location of the particle at time t plus delta t. Sorry, I'm going to call this actually. That's P at time t, that's P at time t plus delta t. So I'm going to write this like this. I have my origin, I have my position vector to the particle at time t, and my position vector to the particle at time t plus delta t. Okay? What is the vector r of t plus delta t minus r of t? That's the vector from where to where? Yes.
It's the vector between both points P.
Yes, and it goes from P of t to P of t plus delta t. So that's that vector. Can anyone think of a good name for that vector? Can anyone think of a good name for this vector? Yes.
Displacement vector.
It's a displacement vector. Now, what is the rate of change with respect to time of the displacement vector? The rate of change with respect to time of the displacement vector. So, if I'm displacing for the same amount of time, if I'm displacing a little bit versus a lot, that has to do with what? For the same amount of time, my displacement varies depending on my velocity. Right. So the velocity is by definition, the rate of change of the displacement. It's the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t, which I can write as dr by dt. That's the derivative of the position vector with respect to time. That's the definition of the velocity of the particle. The velocity vector, which is a vector, which is different than the speed, which is a scalar, which we're going to talk about in a bit. And then what's the acceleration? acceleration vector. That's the time rate of change of the speed. The acceleration is of the velocity, dv by dt. That's by definition. So here that's the velocity vector, and that's the acceleration. Okay. Yes?
I thought for the forces you wouldn't these be vectors?
Yes, but forces are vectors, and also the position vector is a vector, so is the velocity, and so is the acceleration. Right? So we agree that the position vector is a vector because I cannot describe the position of like any one of you with respect to me just by a number. I have to add a direction to it. So it's a vector. The position is a vector. And then the velocity, which is the rate of change of the position, it's a vector divided or multiplied by a scalar, which is a vector. Yes?
But it would be fine just to use the arrow above notation for these?
I would prefer not to, because also we're going to put other accents on top.
Okay.
Yeah. Okay, any other questions? No. Notice that, okay, so if I take this and when dt is very small, when the time is very small, for infinitesimal time, I'll have dr this vector is going to be kind of tangent to the curve. So that's why the velocity, which is dr scaled over dt, is always tangent to the curve. To the trajectory of the particle. Does that make sense? Any questions? So for a particle, we can define its position, velocity, and acceleration vectors. And the velocity vector is always going to be tangent to the trajectory of a particle. Questions? Okay. Let us also define a new quantity called the arc length, coordinate of the vector. So S is the arc length coordinate. It's defined by dr by ds, the magnitude of ds by dt is the magnitude of dr by dt. What is dr by dt? The velocity. So the rate of change of the arc length that's the magnitude of v, which I can call v the speed. So ds by dt is v, the speed. I can also think about this as being ds is the magnitude of dr. What does ds mean? What does s measure? Yes. Yes, so that's ds, and if I sum all the ds's as the particle moves, yes, it's a distance, but what kind of distance am I measuring? Yes? Yes, it's going to be the distance along the curve. So, oops, I keep forgetting this is bad. Okay, so I have my curve, I have my particle at time t, p, at time t plus delta t. if I want to calculate S, here, S of t minus S of t0 is equal to the integral of dr from r of 0 to r of t. So I'm integrating the dr's, not just integrating the dr's, not just integrating meaning summing the dr's. I'm summing the magnitude of the dr's as I go, as the particle moves along the curve. So I'm summing this plus this plus this plus this, the magnitude of the dr's. So what the arc length actually measures is the distance along the curve. S I have a question for you. Is S of t minus S of t0 in general, the arc length between 2 points on the curve, is it equal to the magnitude of r of t minus r of t0? That's r of t. So if I have 2 points along the curve, is the arc length between them equal to the magnitude of the displacement? No, it's not. Right? Because the arc length is this, and the magnitude of this vector is just that, the straight line from between these two. Under which case are these going to be equal? Are the arc length and the magnitude of the displacement vector going to be equal? Under which special case? What is it? Exactly. When the particle moves on the straight line, we call that a rectilinear motion. In rectilinear motion, the arc length, the length traveled along the curve by the particle is the same as the magnitude of the displacement vector. Okay, but otherwise, these two vectors are different. Questions? Questions? Okay. So let me erase the board. So I have a particle with position vector r. Velocity is dr by dt, which I will use the chain rule. So here I'm assuming r is a function of t. But if I write r, instead of writing it as a function of t, I write it as a function of s, arc length, which is a function of t. Under what case can I write? So for every time, I can determine s, the coordinate of the particle along the curve, right? So at time 0, s is this distance. It's 0 if I'm starting from here. And at time t, s is this distance, right? So for every time t, I can find the s coordinate for the curve, as long as I've defined where my origin is along the curve. Under what case can I invert this function? So given s, I can find t. And this goes back to calculus. So for every t, I know what s is. Under what case can I invert the function? Find t in terms of s. Yes?
If the particle doesn't loop over itself anywhere?
Yes, which from math means exactly. So this means that for every s, there corresponds one t. So there's no time where you go back and you have multiple s's. So this means that the function is what? 1 to 1. Then it's an invertible function. So under this case, I can write the position vector instead of t in terms of s of t. And I can use the chain rule, dr hat by ds by dt. ds by dt, that's, I called it the speed, v. So what I'm saying so far is that the velocity vector is the speed times along this direction, dr by ds. So what is dr by ds? What is the magnitude of dr over ds? dr by ds from here. The magnitude of it. If ds is the magnitude of dr. So when I go infinitesimally small, my delta r and my ds, they have approximately the same magnitude when I go very small. Yes? It's a unit vector that points the direction not of r, but of dr. So it's a unit vector that points the direction of what? The velocity. So tangent to the trajectory. Okay? So this here, I'm going to call it ET. ET is a unit vector tangent to curve. Okay? So from before, the velocity vector is tangent to the curve. So the direction of the velocity vector needs to be tangent to the curve. That's why ET is tangent to the curve. And this is a unit vector because dr by ds has the magnitude of dr, the magnitude of ds are equal from the other board over there. Why did I write ET as a lowercase unit vector? Because it moves, exactly. So you can notice that as the particle goes along, travels along the curve, ET is going to change. So at different points on the curve, ET is different. And with my sign convention here, if the particle is going back, then ET is going to flip. So ET is related to the motion of the particle. V is V ET. Questions? Questions, questions, questions? Okay. I will take the derivative of this to calculate the acceleration. So A is the derivative of V. Now, I'm taking the derivative of a vector where does the speed depend on time in general? Yes. Does ET depend on time? Yes. We just said that it's not fixed. So ET depends on time. So when I calculate the derivative of the velocity, I have to use the product rule because that's the product of two functions which depend on time. So V dot ET plus V ET dot. That's the acceleration of a point, of a particle. And I really, really like this form because it tells us two things. The acceleration of a particle is due to two components. One is the change in speed. The other one is a change in what? Direction of the velocity. So the acceleration of a particle is due to the change in the magnitude of the velocity plus the change in the direction of the velocity. So if I have constant acceleration, then I need to be going, could I be going in a circle and have constant acceleration? Sorry, and have zero acceleration? Could I be going in a circle and have zero acceleration? Yes or no? No. Why not? Because even if I'm going on a circle with constant speed and this component of the acceleration is zero, ET is not fixed. ET is changing. So I have an acceleration due to the change in direction of the velocity. Okay? We will talk more about this throughout the class. We'll start on Thursday talking about rectilinear motion along a straight line, and I'll introduce kinetics for a particle. So thank you all for coming. Wishing you a good semester, and see you on the discussion section tomorrow and on Thursday. I have office